All right, so this slide says to give Lewis structures for each of the following. There's several molecules here. So in order to do this, you need to know something about the number of valence electrons in each atom. You can get that by Googling it, I guess, or you could look at the group numbers. Groups 1A have 1, 2A have 2, 3A has 3, 4A 4, 5A 5, 6A 6, 7A 7, 8A 8 valence electrons. And then the other ones you don't need to worry about, essentially. So hydrogen is in group 1A. It has 1 valence electron, so its dot structure has 1 dot. Fluorine is in group 7A, so it's going to have 7 dots. These 2 electrons are going to be shared between each other, and you're going to form HF. Just like that. The next one on there is nitrogen N2. I already did that one for you, so I'll just redraw the Lewis structure for it. It's a triple bond. Like that. All right, and then the third one, CH4, which is methane. Carbon is in group 4, so you're going to have 4 dots for that. 1, 2, 3, 4. And then it has 4 hydrogens. So we've got 1, 2, 3, and 4. Each of those has 1 dot. You're going to get a bond forming between those two, these two, and those two. So methane is going to look like this. Now don't worry about it not being a perfect drawing. It's good enough. But notice there are no lone pairs or 0 non-bonding pairs in methane. All right, the next one on there is, actually I skipped ammonia, so I need to do that. Ammonia, NH3, nitrogen's in group 5. So you've got that, you've got a hydrogen, hydrogen, hydrogen. Each of those are in group 1, so they have 1 dot. We have 1, 2, 3, 4, 5 for the nitrogen. 1, 2, 3 right there. 1 bond, 2 bonds, 3 bonds. And so your nitrogen is going to have 3 atoms bonded to it, 3 single bonds, and it's going to have 2 lone pairs on it in ammonia. Next, we have carbon tetrafluoride. I'm going to actually erase the ammonia here because there's so much, but the carbon tetrafluoride, you have carbon in group 4. The fluorine is in group 7, and there's 4 of them. 1, 2, 3, 4. Since fluorine has 7, there's going to be 7 dots on each. And there's going to be 4 dots on the carbon. So we've got 1 bond, 2 bonds, 3 bonds, and 4 bonds. And so carbon tetrachloride is going to look like this. 1, 2, 3, 4 single bonds, and then each fluorine is going to have 3 lone pairs. Now in reality, all these lone pairs get tedious and they still make a mess of it. So an actual real chemist is going to ignore it and we could just write this. It's implied that the fluorines have to have the lone pairs. Fluorine atoms can only form one bond anyways, so they always have 3 lone pairs, so why even put them in? But for your sake, it's good to have them there. All right, the next one is NO+. So nitrogen has 5 electrons. It's in group 5. Oxygen has 6 because it's in group 6. And I'm going to put those in like this. So we have 1, 2, 3, 4, 5 on the nitrogen. 1, 2, 3, 4, let's say 5 and 6 on the oxygen. But this has a plus charge, and so because of that, I'm going to just eliminate that dot there. And so we have 1, 2, and 3 bonds. So NO, nitric oxide, nitrogen monoxide, is going to be a triple bond with a lone pair on each atom. I've already done O2 for you. O2 has a double bond and then a lone and 2 lone pairs on each oxygen atom. Now, if you haven't figured out, in all of these examples, every single atom has 8 total electrons on them. The oxygen atom here has 2, 4, and then we count both electrons in a bond being on both atoms at the same time. So 2 and 4 more. So 2, 2, 4, and then the lone pairs 6 and 8. The other oxygen has 2, 4, and then there's 6 and 8 right there. So they each have 8 valence electrons surrounding them, so they follow the octet rule. Carbon monoxide, we've got carbon, which has 4 electrons around it, oxygen, which has 6. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And our bonds, we're going to have 1, 2, and what? Uh-oh. What do we do? Well, basically for this, if you're using the dot structures, it doesn't work. This is another reason why I don't particularly like to use dot structures, but this is what your book does. There's actually a better way to do it. But what actually happens is that, let's just say these 2 electrons, they're going to form a triple bond there, and then these 2 electrons, they're actually going to pair together. So they kind of go together. And then this, you have C, 1, 2, 3. There's your oxygen. You've got 1 lone pair there still on the right. You've got the lone pair there on the left, which I'm going to highlight in the same sense. We've got the red electrons there and the 2 blue ones right there. This isn't really what happens, but it's how it has to work. All right, exceptions to the octet rule. Sometimes atoms don't have a total of 8, they have less than 8, or sometimes they can have more than 8. But this is not a common occurrence, and there's a good explanation for why they can happen. First one on here is BF3, boron trifluoride. And so boron has 3 electrons around it. The fluorines each have 7. So 1, 2, 3 around the boron. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then we're going to have 1 bond, 2 bonds, and 3 bonds. And so we get this right here. All right, so the fluorines all have 8 electrons around them, 3 lone pairs and 1 bonding pair. But if you look at the boron, this atom only has 3 bonding pairs. Therefore, only 6 valence electrons. And that's actually normally frowny face, but it's okay here. And the reason is that boron only had 3 valence electrons to begin with, meaning it can only form 3 bonds, so it has to have an empty space in a sense. There's nothing else it can do. The next one on there is SF6. So you can just see right off the bat the sulfur is bonded to 6 fluorines. So if we draw that, it's going to just ultimately look like this. Each fluorine is going to have 3 lone pairs on them. As it always does. The sulfur, which is in group 6, has an electron configuration of 1s2. Actually, let me use it in shorthand notation. It is equal to neon, and then 3s2, 3p4. So that means it has 6 valence electrons itself. Which we normally could do something like that. But what is actually missing from here, this electron configuration, is that it actually could be written like this: 3s2, 3p4, 3d0. There's your valence shell in its entirety. Sulfur has empty d orbitals. And so sulfur can violate the octet rule because it can put the 9th and 10th and 11th and 12th electrons into d orbitals that it has. And so it's going to violate that. So to quicken this up, I'll just do the rest. PCl5 is an example of an exception to the octet rule. For the same reason sulfur is, phosphorus can expand its octet by using d orbitals, but PCl5 is going to look like this. Each chlorine is going to have 3 lone pairs on it. ClF3, chloron trifluoride, is going to look like this. Not to get into the nitty-gritty details, but it's going to look something like this. Explanation again, chlorine has empty d orbitals that it can use to expand its octet. If you look closely at this, the chlorine atom has 2, 4, 6, 8, and 10 electrons around it. 2, 4, 6, 8, 10 electrons around that phosphorus. Radon dichloride would look like this. So we've got So you can see the radon atom actually has a whole bunch of electrons around it. It has 2, 4, 6, 8, and 10 around it. Radon dichloride, which does exist, has empty d orbitals in it in the radon atom that it can use to expand its octet. Beryllium dichloride, BeCl2, looks like this. And that's it. Beryllium has just 2 valence electrons to begin with. So it has just those. It can only form 2 bonds. It only, therefore, has 4 valence electrons. And finally, iodine tetrachloride is going to look like this. And now it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 electrons that are non-bonding, plus 8 electrons that are bonding right there. That's 32. But there's 36 electrons in this species since you have that charge there. Each of the atoms has 7, and there's 5 of them, which would make 35. So you have 1, 2, 3, 4. I should actually do those in red to kind of. Now, if you add those are on the iodine atom. So you have 2, 4, 6, 8, 10, 12 electrons around the iodine. Iodine, again, has empty d orbitals it can use to put these electrons in.